So yeah, I wanted to welcome all of you. It's a great pleasure to see all of you and showing your interest in coming to the University of Utah. I'm so sorry that, I mean, this year has been really, really difficult for almost everybody to make it through. I assume all of you have had your challenges, whether in school, possibly family, business, whatever, to make it through. And so it's wonderful that you still keep, you know, your advanced degrees inside and pursue that. And I promise you that, you know, a few years from now, all of this will be in the rearview mirror, and you'll remember it as one of the stories you can tell. And you know, every crisis is an opportunity as well. So, you know, we'll all together find solutions to address that. It's a little unfortunate. Utah is really a wonderful place, just as a place to live, to study, to experience. When I was in my graduate studies, which was a long time ago in the mid-90s, I ended up by pure chance at the University of Utah. And actually, because I originally had an offer from somebody at MIT, and you know, coming from a European school, most of the US only consists of the top schools on the East and the West Coast. And unfortunately, that faculty ran out of funding about 3 or 4 months before I was supposed to start. And then he sent me an email at that time and said, you know, you can still come, but I can't really have you work in the clean room. My background is in solid state devices. I'm an experimentalist. I'm not a theory person. And I'm much more of an engineer than I'm a basic scientist. So I build stuff that I make work. And so I was quite down. I was wondering what to do. And then a friend of mine had been in material science, and Utah has a very, very long history at strength in material science, in computer engineering, imaging, in entrepreneurship as well. And so he said, well, why don't you go there? And so I ended up here by pure chance. And I was so surprised by how friendly people are, how beautiful the entire environment. I mean, the campus is really stunning. I was able to live walking distance with a very, 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 very tight budget at that time from campus. I was able to enjoy activities like skiing and hiking and rafting for comparably little money. And so I kept all those memories. I ended up going back to Europe, started my first business. And then in 2003, 2004 was hired back on faculty. And the moment I stepped back on campus during my interviews, I knew that I wished nothing more than to be here. And some of that has stayed with me against a lot of offers to go somewhere else. My background is in solid state devices. I ended up focusing most of my career on looking at implantable devices. And really the motivating factor was that I thought I could help people with that. You know, I've had a lot of exposure to tetraplegics, people with amputations when I was younger already. And I felt, and I was already in the, you know, early 90s, late 80s, early 90s, that it was unacceptable that as a society that is so advanced, we couldn't do better. 27 years later, I'm still at it. So according to my wife, I'm just very stubborn and slow. But you know, it's something where, as an electrical engineer, you have so many opportunities, and you will figure that out. Almost all the major areas that impact society, from energy, renewable energy, logistics with transportation, healthcare applications, AI, robotics, the machine learning side, quantum information processing, everything is electrical engineering inside. And so if you get a degree in that field, that opens so many doors for you in areas you can go into. And, you know, of course, there's the academic and industry tracks, but then within those, there's so many different fields. And you know, you could be working for a company that builds a new advanced sensor for something, or you could be working in a company that sources these and builds bigger systems, or builds things for a hospital. You can transition into the finance sector. You can start your own company. There's actually a lot of students who start their own businesses, sometimes with faculty or on their own. We're very supportive of that. We have entrepreneurship courses and project options. And so there are a lot of ways. And even if your plan is never to have the worries of an entrepreneur and run your own company, you will still learn a lot of skills that may be immensely valuable, because in addition to a very solid education in your field of specialty and a broad understanding of how things are connected, you will also understand what makes the difference between an innovation that is successful and one that isn't. You know, just think of it. Most of you are used to smartphones these days. I don't know, and we take it for granted. It's like an extended brain of ours, and people like Elon Musk and others are now dreaming about implanting all of that to make it even faster. But when you think about it, I remember in the, I think it was around 98 or so, Nokia, which at that time was the biggest cell phone maker, had an idea to build something like this. And they came up with something that was pretty large, you know, about this size here, opened up, and everybody, and it could do email, it could do rudimentary, very early internet, etc. The only people that had were like top C-level managers at big corporate companies that everybody felt you're just trying to look important and show off, but who needs that? And, you know, it's very interesting to understand why that failed. And a few years later, somebody by the name of Steve Jobs takes that concept and says, you know what, that's how I can make this work. And this is how I can market it. And that's the price point, and that's the audience. And no, it is not a specialty tool for a handful of people. I want to make sure everybody's going to get it. Just like, you know, the CEO of IBM, I think in 1954, when asked to estimate the market for personal computers worldwide, and he said between 50 and 100, not million, 50 to 100. So I think it is very, very important to understand these things, and it broadens your understanding. Now, the interesting thing is, as an electrical engineer with a strong math and physics background and systems and how you describe them, you will realize that a lot of the same differential equations that didn't make sense in your undergraduate studies show up everywhere. You can transfer systems from a financial into a fluidic, into an electrical system, whatever. And then these things become fun. And the sort of things I still very much remember in my first semester when, you know, the professor would stand at the board, they were still using chalk then. And, you know, and then he said, let's assume the solution is of the following form. And everything magically works out. And you're sitting there going, how, why, what just happened? And then eventually, after many years, you realize, of course, there are patterns and things that you can recognize. And so, yeah, you can see the excitement here. I'm almost a little bit jealous, but in a positive way, every time that I see people that are at that watershed in their development and they have the opportunity to just start anew. And maybe that's a reason why it pulled me back into the university. I'm still an entrepreneur. I still run my businesses on the side, but my passion is really being here, finding new things, solving problems, helping the next generation of engineers to go on that path, and being able to just be constantly challenged and find new things. Every beginning has a lot of wonder in it, and you're at that stage. So keep that momentum, because there'll always be hard times. Every one of us and everybody who does a PhD will tell you there are times where you want to give up so badly. You've had enough, you want to run away, and you will make it through that. You know, part of it is the endurance. And so, again, I would so much love to show you the labs, the facilities, the campus here. And, you know, maybe there's ways we can follow up with some virtual tours for some of you, if that is possible. But yeah, it's a wonderful place. The faculty here are world-class, students are wonderful, and you have a lot of opportunities to do groundbreaking work in many areas. We've got a few of our faculty here. A few final words. As a department, we've grown a lot. The college itself, and Dr. Berardi Sensala Rodriguez will be talking about that. You know, when I started, the college was at 20 million in expenditures. Now we're at 100 million. The department has grown to almost 40 tenure track faculty. and we're very well connected across areas. Most of us have adjunct positions in many different areas, and so you'll find plenty of opportunities. I wish you the best of luck, no matter what you're doing. I hope we can convince you to seriously consider us as a place that can really kickstart your careers. And yeah, please interact with the faculty here. Don't hesitate to ask any questions. You can also email me directly if you'd want to do any follow-up separately at a later stage. Always there. And we're excited that you've applied and that you're interested in coming here. Thank you very much.
Okay, so I would like to welcome you again to our virtual graduate open house. And for those of you who are out of the country, first I'm going to start by introducing where we are. The University of Utah is located in Salt Lake City, the capital of the region of the US. Salt Lake is a really nice city with lots of things to do. It's like we have the outdoors right, let's call it next door to where we live. And this is something that is basically surrounding us, both in the summer as well as in the winter. This is a place where there are lots of things to do and where one can greatly enjoy nature. Also, the city itself has all the advantage and nice things of a large city. So you can find a thriving cultural life, lots of stuff to do. We have great sports. So overall, in all, this is one of the nicest places that I can imagine where one can live. And this is where our university is located. This is a picture of our campus that is actually a really nice campus. Is as you can see here, right at the, let's call it, edge of the city, but also embedded in the middle of the city. One can just go out of office, out of the lab, and enjoy the outdoors right out from campus. The campus is very walking friendly and is a very nice place where to work and also live. Um, Here is where our department, the electrical and computer engineering department, is located. We are part of the College of Engineering, and we are here in the US in terms of research power among the top universities. Our research expenditures in engineering have been substantially increasing over the last, actually at this point, couple of decades. And they are at the level of $100 million per year in terms of research expenditures. That means that we have large and important research groups, and we have programs that tackle all the main areas related to electrical engineering and its applications. These are pictures of some of our, for instance, buildings where electrical and computer engineering faculty and students work. We have two buildings where we have labs, Manuel Engineering Building and Sorenson Molecular Biotechnology Building. This is where our nanofab is located. And here in Manuel Engineering Building is where most of the research labs are located. So in terms of facilities, we have world-class facilities, and pretty much we can work in all the type of problems, both theoretically, computationally, as well as experimental, that you can imagine. In terms of faculty, we have 36 and more coming faculty that are very research active, and we tackle many areas from communications, image processing, and signal processing, power control, robotics, computer engineering and VLSI, electronic circuits and systems, both from an analog and digital perspective, We have also a strong group on electronics and solid state, ranging from the materials to the devices and systems. And we are also very research active on the areas of electromagnetics, from the theoretical to the practical aspects, as well as optics and electronics. And I suggest you to look in our department webpage about who are the faculty and what are their main research interests in their labs. Regarding our program, you can find most of the information in the graduate program webpage. This is the link, for instance, to the admissions webpage, but you can find also all the details about the application process, as well as the requirements. Is like not just application, but also degree requirements in our webpage. Sean will go through more detail about what we are expecting and what are the deadlines of our programs, but I would like to mention that we have several programs. We have a MS, an online MS that can be done in principle fully online, as well as we have a PhD program. And for the PhD program, all our students are basically financially supported by the department. And this is something very important. You don't need to pay anything. We pay you for all your needs. It's like students typically are supported mostly as research assistants in research process, but also as DAs. And starting next year, we are going to start a fellowship program where first year students will be able to come being unaffiliated for a first year with a particular research lab and be exploring the research opportunities in the different labs before making the decision of, let's call it, it's like finding a formal permanent advisor. So this is something that is going to bring lots of flexibility, and this, let's call it, is like decisions for fellowship. We're going to automatically consider all the applicants to the program, and we're going to select the tops for that program. So with this in mind, I'm going to let Sean continue.
I'm John Bolke. I'm the graduate coordinator, and I'm fortunate to be the one guy who gets to process all of your applications. This is perhaps the funnest part of my job. I absolutely love what I've been doing. I've been working as an advisor for 20 years. I love to be able to watch people change their lives. The students that come into our program have fantastic opportunities. They get hired by Google, by Apple, by Facebook, by Amazon, large tech companies, Intel. They seem to have fantastic unlimited resources and opportunities. And it's great to be able to watch a student transition from the very beginning of inquiring about the program to telling me about their awesome job they just got. One important thing is that all communication and emails should come through me because I'm the point of contact through the application process. Our faculty and staff are very busy, and so we ask you please don't email them constantly asking if you've been accepted yet. It does take some time, but it's important to note that I'm not a decision maker. We have a graduate committee that reviews those applications. We have a diverse group here. We have people that are doing the master's and PhD programs, and I think it's good to see the complexity and differences between those. If you apply for the master's degree, it's most likely that you will not receive funding. We have tons of applicants, and we are invested in putting together many PhD students who are doing long-term research for us. And so we don't have a lot of funding. If you are interested in applying for the master's program, it's important for you to know that. However, many students that do accept a master's program, once they arrive here, take a few classes, meet with the faculty, they are able to find research assistant jobs, and there are teaching assistant jobs available for them. But I just want to put that out front. It's not a guarantee that you will find something in the master's degree. Now with the PhD process is a little bit different. The first 4 steps are the same, but once our committee of 7 PhD faculty have approved the applications, we send that list to our faculty, and the faculty then schedule interviews and meet with the students and talk with them about their research and see if it would be a good fit for them. After a faculty have interviewed several different people, they'll make a decision and they'll contact me to draft an offer letter. And then that draft offer letter will include health insurance and the details of what we anticipate your pay will be for the next year. And so then after you're admitted and accept an offer, I send it to the university admissions office. They review the applications to see if they are able to ensure they have the transcript is what we're looking for. Now, if you're an international student and you're looking at applying, the reason why we start back in January is to give you enough time to go through these 12 steps. Our international PhD applications, we have quite a few of them, and I'm an expert. I work closely with our visa application process. But just so you know that once you're accepted to the program, they have the additional steps of getting an I-20 and also embassy scheduling appointment and getting your visa approved and flying here, and then getting a social security numbers. And so the international PhD process is long. It does take time. This process does take anywhere from 4 to 6 months. Unfortunately, with COVID this last year, we had some unique challenges where many students were not able to schedule embassy appointments. The embassies are now open and taking appointments, and we're hoping that the people that are attending this meeting tonight, that you will be able to get here by the fall 2021. Just so you know, some of the requirements, it's important that you finish the application as well as be able to pay the application fee. If you're a domestic student, and you're applying for the PhD, it is free. For the master's, it's $30. For our international students, I'm sorry, there's a little additional cost, but also pays for the employees that work on completing the I-20s and the visa processing, as well as the database administration. And so the admissions office, beyond my control, has agreed that they're going to be increasing the cost for the application process. So I encourage you to apply before January 1st to save some money. You can look at my homepage and see information about that. But just so you know, when you do apply, I encourage you to have a copy of your transcript in advance. You can do an unofficial transcript, but if you are accepted, you are required to have your official transcript. We also encourage you to get 3 letters of recommendation. You don't actually have to get a physical letter yourself, just email faculty or friend or coworkers or supervisor in advance and let them know that you're applying to the graduate program. And when you apply and hit a submit button, it will trigger an email to be sent to them. And so you don't have to go chasing those emails or letters down. You just have to provide that name and contact information. We also encourage you to have a resume or a CV, which includes any research publications, as well as a statement of purpose. And you can keep it very short and just tell us a little bit about why you want to do a PhD or a master's program. Also, another great new change that's happened with our university is we have the Gre Waiver. Unfortunately, with COVID, we were not able to administer the Gre exam. Our graduate committee reviewed what was going on around the country, and we discussed it, and we felt that our students are most successful that graduated from ABET accredited schools. And so these are the larger schools in the local area, such as University of Utah, BYU Idaho, Utah State, Weber State. Most Pac-12 schools and major institutions are all part of the ABET accreditation. It's a national standard that we work with. And so I'm happy to report that if you did graduate with your bachelor's degree from any one of those schools, or even graduate with a master's degree from an ABET accredited school, you don't have to take the Gre exam. For our international students, it is difficult for us to be able to have the compare them side by side. Fortunately, our faculty do have the ability to be able to know and be familiar with many of the international schools and how qualified they are. And so if you are applying from an international location and you would like to try to have your transcript evaluated for the GRE waiver, please feel free to reach out to me. I evaluate these on a regular basis, and our faculty are pretty familiar with these, and we can get those approved for you. So, don't stress out if you're unable to take the GRE. However, if you can, it does help expedite the process if you can do that. So I encourage you, if you have taken the GRE, you should do that. For our international applicants, you are required to do the Toefl exam. The Toefl exam, you must have at least a score of 80 or higher, and our department likes to have students around 100 just to ensure that you can be prepared to be successful in our program. Berardi also mentioned earlier tuition benefits. Part of that is you're required to work at least 20 hours a week for the university, but the benefit is that you qualify for your tuition. Your tuition is paid for, so you can save yourself tens of thousands of dollars by applying to our PhD program and working for us. We are looking for great talent as teaching assistants and research assistants, and 80% of your health insurance is covered when you qualify for the tuition benefits, and 20% of it is paid for by you, and that's fairly typical for any employment. That students have to pay some part of their health insurance, and it also includes the dental insurance as well. Some students are always worried about when they get here if they're going to find a place to stay. I've never had a problem ever with people being able to find a place to stay. Most of our on-campus housing is very convenient. We have shuttle buses that circle the campus every 15 minutes. You can jump on a bus and get nearly anywhere you want to go. And also we have athletic gyms that are fantastic with giant rock climbing walls and meal plans. We also have off-campus housing, which is pretty cheap. And also you qualify for a bus pass. If you are an active student here, you get a free bus pass with tracks. And right along our mass transit system are many inexpensive apartments. And so you can be 20 minutes away from campus and still ride the tracks everywhere you need to go and not have to pay for it. What I recommend for students who are planning who do arrive, don't just buy something you find on the internet. Usually those are a little bit more expensive because they can advertise. Once you get here, you can shop around, just rent an Airbnb and bed and breakfast, and you can usually find apartments. Don't stress out about that aspect of it. Once you get it here and meet with me, I can usually help you find a place to stay fairly easily. And so that's just a little bit about the application process. I'll answer some more questions or look through the chat after I stop talking, but I'm going to turn the time back over to Berardi, who's going to talk a little bit about some of his research.
Okay, and I'm going to start with this short presentation, giving an overview of the research group that I lead. Basically, I lead the Terahertz Optoelectronics research group here at the University of Utah. And my group is quite, let's call it, medium to large size group. I have 2 postdocs and 6 PhD students working with me. We try to tackle problems both from I'm gonna say is like theoretical computation as well as a practical manner. And these are some keywords that may classify the research in my lab. Our research lies at the intersection between electronics, photonics, optics, material science, and computing. So from this perspective, the work that we do is intrinsically multidisciplinary, and we collaborate a lot with faculty in this department, as well as in the school, as well as in other universities worldwide in the research projects that we carry on. Our primary interest lies in technologies, basically operating is like at the long wavelength region of the electromagnetic spectrum. Basically, we work types of problems ranging from the device to the system levels, as well as we employ and often develop new materials for these applications. I have a quite sizable research enterprise, and our research is supported by many funding agencies as well as industry. I am all the time looking for new students, and I like students basically with any background. I think that anyone with any background can contribute to the type of research that we do. So if your background is not exactly in optics, electronics, electromagnetics, it's like if it's, for instance, it's like computer science, mathematics, it's like you are more than welcome in contributing to our research, because we have interest in all these areas. Okay. Some recent highlights that kind of show the type of work that we do. We have been recently using machine learning as a way to enable the smallest nanophotonic devices. This is something that we work together with Professor Menon, that is going to present later on the research of his group. Here we basically employed a reinforced learning algorithm that we developed for the design of ultra compact photonic structures. This is an example of basically a splitter, and we have shown that we can make these devices very, very small, the smallest ever, let's call it, proposed, and with a performance that is, let's call it, similar to what is possible otherwise. And here we're trying to take this approach and extrapolate it to the design not just of passive but also active devices. So this way, like the same way that Moore's law has evolved in electronics, we can make very large and complex circuits on a chip based on photonics. So this is something that I am very interested in, and where we have lots of research projects and opportunities. Another aspect where I'm very interested is on fundamental aspects of new materials for all these applications, ranging from RF to optical applications. Here we have been exploring new materials, and an example is cadmium arsenide. This is a 3D Dirac semi-metal, a 3D material that is analog to graphene. And materials like this possess an interesting properties, that is that intrinsically they offer what we call kinetic inductance. This material behaves electrically, is like not just as a conductor, but also provides inductance, and this arises from the electron inertia in this material. We have harnessed this property, for instance, to make very compact inductors and LC resonators, and this could operate quite effectively even at very large frequencies. That this is a challenge with, let's call it, traditional materials. We have also demonstrated that these devices can, one can alter these properties very fast. And this is something that is very important, for instance, if we want to make active reconfigurable devices based on these materials. So this is a research area where I'm very much interested, and where I see that there are lots of opportunities to transform completely the field of electronics and bring it to next levels. Okay, so this is a quick overview, and feel free to contact me if you have interest in my group, our research, and as I mentioned, I'm always looking for talented and motivated students. Thanks. And with this, I think Rajesh is the next speaker.
Well, welcome everybody. My name is Rajesh Menon. I'll be very quick. My group website is at the bottom, lons.utah.edu, so you can find all the information there. I would start off by saying we're looking for the best students to tackle some of the world's biggest problems. And specifically, my group works on a pretty big range of problems, ranging from As you can see on the top left, 2D and 3D nanofabrication. So how do we make structures that are extremely small in a scalable manner, which of course is applicable to manufacturing in general, advanced manufacturing, which is very critical for the infrastructure for our country. On the right, next to it, I have a bullet called Computational Nanophotonics, where we have combined computer science principles with nanofabrication to enable photonics devices that have never been demonstrated before. So they're essentially world record devices. Moving on, we also work on various kinds of computational imaging. This essentially means if you think about the vast majority of images and videos that are taken today will never actually be seen by a human being. They will only be seen by a machine. Then we need to really rethink what a camera is. It raises lots of very interesting philosophical questions, but our approach is primarily driven by information theory. So we apply principles of information theory and essentially some basic mathematics with optics to come up with cameras that are essentially what we call non-human cameras, enabling superhuman capabilities. Moving on, we also work in biology on imaging deep inside the brain, primarily the mouse brain, but also a few other animal species as well. We build very, very small microscopes to be able to see deep inside the brain with the goal of understanding neural networks and particularly physiological behavior. And these are experiments done in collaboration with the neuroscientists, both in Utah and also around the world. We collaborate very widely. More recently, we've been working on quantum photonics and optics, where we are looking at fairly fundamental studies of understanding questions about quantum measurements, uncertainty principle, and so on, all the way to more applications such as integrated photonics for quantum cryptography and communications. So in a nutshell, we work on nanofabrication, machine learning, and related algorithms, various optics and photonics devices, ranging from fundamental studies to applications. And again, we are looking for truly excellent students who are really interested in working hard and making a huge impact on whatever project they prefer to work on. Feel free to contact me on my website. Thank you.
Okay, so hello everyone. This is Wei Lu. I'm a new assistant professor in the Department of Electrical Computer Engineering, and I'm starting my lab. And for sure, I'm looking for the best students to join my lab. So my research is about, in the very broad sense, to study the light and matter interaction at the nanoscale. So we are engineers and scientists and try to design the better photonics, optoelectronic devices using the weird nanotechnology, I would say. So yeah, we are aiming to using photonics to design the better devices for the computing, for the communication, and for the quantum technology, and for the health application as well. So first, I would like to echo what Florian have ever said about the multidisciplinary nature of the research in electrical and computer engineering. So before joining the U, I have been working in the company, in the startup company, designing the photonic devices for the AI accelerators. So where I have been working with a team of talented scientists of engineering from a very diverse background. I have been working with the physicists studying the dark matters, the physicists studying the computer, quantum chemistry, and the digital designers and the physical designers, and analog designers, and packaging engineers. So you can also see that this is this type of multidisciplinary research has been reflected in the many research here in the many groups. So for me, I have been focusing on the three aspects of my research. The first is about reconfigurable photonics. So in this area, we study the materials and use new materials to design devices and build systems out of that for the optical computing and artificial intelligence. And with the evaluation of systems, we can further optimize the materials and devices. So this closed loop style can really build the high performance, the hardware accelerators for the AI. And my second research area focused on the ultra strong coupling physics between the light and the matter. So more specifically, I will study the exciton physics in the nanomaterials when it is coupled to the photons in the cavities. So the properties I'm looking at is the ground state properties of these materials. So when you put the materials inside the cavity, how the fundamental properties of these materials will change so that you can build a better and new devices out of that, and which can find applications in quantum optics and quantum chemistry by designing the cavities and the materials. So the third area I'm working on right now is the terahertz sensing. So by designing the better and new technology using the AI and the quantum technology, so I'm aiming to design the better and ultra sensitive sensors in the terahertz for the bio and chemical molecule detections. So if you want to know more details, you can go to my group website. And if you're interested in any of areas you want to know more about my research, you can feel free to email me. And I said I'm looking for the best students to join my lab. So just feel free to email me if you have any questions. Thanks.
Hey, hi, hello everyone. My name is Benjamin Sanchez. I started my lab at the U this past summer, before summer, talking about multidisciplinary background and experiences. I was at Harvard Medical School in a lab where I was the only engineer and the rest of the people were medical doctors. So that should give you an idea of how interdisciplinary is the kind of research we do. And particularly, I would like to talk a little bit of the research interest of my lab. And so what we do in my lab is we leverage electromagnetics to solve fundamental biophysical problems that give us insight into complex biological systems. And we use that information to develop novel medical devices that we can use to monitor and measure health, and ultimately to provide medically accurate data. So this is my website. Please feel free if you're interested in learning more about the projects that we are starting. It's all the information is over there. I'm just gonna touch base on one that I'm particularly really excited about, is this piece of hardware that we have designed over the past years. This morning, someone was wondering if there were software developments or research going on in our program. And just to get you a sense, I didn't say that this morning, but there are over 50,000 lines of code in this hardware on the left, just so that you get an idea. And surprisingly, it compiles. So this piece of hardware basically allows us to collect electrocardiogram activity and plot that data over the internet in real time. And now we are currently working with our partners, Texas Instruments, a global US semiconductor company, and Be Secure in North Ireland, to integrate some of those features into a wearable device, in this case it's a smartwatch, for stress and anxiety monitoring, which it's actually a huge deal right now. And yes, that's where things stand. Just so that you have a sense as what I meant before. Here you can see a video of my web browser where we see in real time the ECG of a person, and that person doesn't necessarily have to be in the next in the next room. It can be pretty much anywhere in the world. And so we do even more than just measuring ECG. We can detect the heart rate and classify the beat activity of those subjects. And that information is sent over the internet with an Internet of Things protocol to a cloud-based server where we can display that information in real time. And now we are at the door of starting to do big data analytics with data collected from all over the place. And so if any of this sounds interesting to you, and if I can move to the next slide. Yes, if any of this is of interest to you, or you want to learn more about other projects that we are currently starting, please go to my website and shoot me an email. And yes, I'm also looking for people and have funding available. So looking forward to hearing from you. Thank you so much.
My name is Hae-Young Yoon. We do lots of experimental parts. As you saw a few minutes ago, Florian talked about the great facilities and the wonderful research that we do at the University of Utah here. And Barati showed you nice nanophysics facilities. My group, we do utilize those systems a lot. Specifically, we are interested in the renewable energies. So here shows some of the examples. We want to make very lightweight and flexible solar energy devices that can actually go to these Earth applications, like small devices like ITO, or some flexible electronics, or the smart systems, as well as it can be the real power generation for our cities and homes. Like some of you may have a solar panel on your roof right now. The efficiencies the current technology has right now is a little bit lower than what we can actually achieve in the future. So what we do in here, as you can see in this second image, we try to understand these nanostructures or microstructures of the materials, and then connect those properties by engineering, the nano-engineering of the materials to make the device that can be integrated in the real system. So we are trying to reaching out these material parts to the system level. We do many different types of solar cells, but we are very, very much interested in these lightweight and flexible devices. The reason is we want to go to not only these Earth applications, we want to go to the outside of the space. For example, I'm not so sure if you can see in here in my house, over there, I always remind myself the space, because we are bound on this Earth, but there's a lot of opportunities outside of the Earth. But if we bring the materials or devices, we need to power them. How are you going to do it? So we want to make some feasible energy source based on the solar energies. That's what we are trying to do it. Another new approach that we are trying to work with several collaborators, particularly in our department, we are creating some sensors by engineering the interfaces. So I haven't showed up in here, but we are using very flexible pillar array solar cells or pillar array sensors that can detect some of the biomedical species, so that you can use that one as a sensor, at the same time use it as a solar cell. So that's what we are trying to do it in our department. So I think that's a major part we are doing it. Oh, I have to mention that one for sure. So as Rajesh Menon said that we do lots of work in the nanofab. We love to have students who are really, really motivated in their research, because we do a little more work sometimes than other groups. So if you are really, really highly motivated students, currently we have 2 DOE fundings, Department of Energy fundings, so they can support you when you start your program right away. So feel free to contact me if you have any questions. Thank you.
Thank you. Yeah. So hello, everyone. My name is Darren Young. I am one of the professors with the Electrical and Computer Engineering Department here at the University of Utah. I direct a research lab I call a Wireless Microsystem Laboratory. And, my email is darren.young@utah.edu. If you are ever interested, in my research work, feel free to shoot me an email directly. John, could you go to the next slide? All right, thank you. So let me just give you a quick kind of a rundown of my research lab by telling you the focus of my research lab. My research work mainly focusing on integrating advanced sensors, actuators, and a low power mixed signal integrated circuits at a system level to achieve autonomous sensing and wireless communication capability for critical applications. So I'm kind of come from a different side of electrical engineering, not so much on optics, materials, or, things that you have seen up to this point. I came from semiconductor sensors, actuators, and IC designs. And specifically, when you look at critical application, you may wonder, what is critical application, right? You can define critical applications in many different ways. The way I define critical applications, at least for my interest in my lab, is, those applications require small size, lightweight, low power dissipation, and often, for application that we call a batteryless operation, and also require limited wiring access, such as biomedical implants, wearable sensing, personal navigation, environmental monitoring, as well as industrial sensing applications. John, could you go to the next slide?
Yep.
Yeah, thank you. Yeah, so this slide shows, the next slide, I have 2 more remaining slides, kind of give you a picture of the projects that either have been completed in my research lab, by my PhD students, or ongoing projects. The very top one shows that, we worked on using micro electromechanical sensors coupled with, 2mm by 2mm low power circuits, combine them together, put inside your, into middle ear, not necessarily your middle ear. For example, a deaf person's middle ear, to build an implantable microphone. And the second one from the top is a wireless implantable EMG sensors that we can tap off the EMG signal from the muscle in the residual limb, use that to control intelligent prosthetic limb operation. And the third one from the top is a wireless blood pressure sensor. And also, in this picture, you can see that in the left side of the system, we have a little tiny chip that does the pressure sensing, as well as charging up a implantable battery surrounded by ferrites, with coils that can be implanted under the mucosal layer of a person. For example, a patient that suffers from urinary incontinence, to measure its blood pressure. And the last picture down there is a very interesting project, actually. One of my PhD students worked on using micro electromechanical sensors, pressure sensors, with his own custom designed CMOS low power circuits, put them together, build a fully functional device that can be put inside a live laboratory mouse that can be freely running inside a cage without any wire attached to it. And there's no battery inside that mouse. We're relying on, radio frequency power transfer from bottom of the cage to a power receiving device that's built as a part of the system inside the animal's body to sense its real-time blood pressure information. John, could you go to the next slide? Yeah, this is my last slide showing some of the ongoing research project in my lab currently. On the very top, we have built something called a small shoe-based personal navigation system without GPS. You probably can see from the upper hand left corner, there's a very flexible, tactile sensor array that one of my PhD students built, coupled with a CMOS chip. We put these devices together with, other sensors such as IMU sensors, accelerometers, gyroscope, all inside a shoe. When a person wears this type of small shoe, he or she can walk around in the park or in the city without GPS signal. And we have demonstrated performance such as, one of my graduate students walked in a park called the Liberty Park in Salt Lake City, over 3,000 meters, and the accuracy, let's say that the position area is no more than 5.5 meters. In the middle is a implantable glucose sensor. Due to the time limitation, I won't get into the detail. You can see, one of my graduate students wearing this nice clean blue glove, holding that a prototype device. And on the right side of it, it is a CMOS chip that we designed. So I came from the circuit design background. And the chip has a 3 millimeter by 3 millimeter. More specifically, I think you can see maybe 3.3 by 3.3, but we're only using a small area, in the middle of that chip. It's about 1 millimeter by 1 millimeter, containing all the low power circuitry that is needed to receive power from outside the body, does the glucose sensing, take the data, digitize it, and transmit from inside the body to outside the body. At the bottom, it's another ongoing research project in my research lab. It's called wearable skin patch, health monitoring. It's very similar to, Professor Ben showed earlier, right? Is we're building something called a flexible skin patch that coupled with a low power CMOS chip that can detect real-time blood pressure signals, sort of indicating irregular heartbeats, and our demonstrated accuracy is within 99% compared to ECG signals. So this gives you a kind of a high level picture of what type of research is going on in my lab. I'm mainly focusing on sensors, low power circuits for specific applications. I'm always looking for highly motivated students. If you are interested in this type of area, feel free to contact me. Thank you.
Okay.
Wow. Hi, everyone. I'm Daniel Drew. I'm an incoming professor, so I would be starting with all of you in fall 2021. I actually went after Darren this morning, and that time he had props for every single one of his amazing projects. So he's taking it easy on me this time.
No, you are good. You better than me. I guarantee.
I appreciate that. So I'm working towards a future filled with ubiquitous insect scale robots, and that is a systems level undertaking that combines a number of electrical engineering topics, including MEMS, microfabrication, control of swarms, and basic autonomy, which includes power autonomy as well as the controls for how do we realize that. My research to get there largely involves these three thrusts, which is development of novel mechanisms, development of multifunctional components that overcome the resource constraints at scale, and the development of ecosystems, the surrounding infrastructure that enables these small robots to exist long-term in their environment. Now, just touching on different topics there, propulsion at the millimeter and centimeter scale is extremely difficult. Existing robotic actuators begin to fail. You may have seen some biomimetic solutions, ones with flapping wings that replicate insects. My work is completely different. We microfabricate using MEMS technology, atmospheric ion thrusters. So these produce ions, accelerate them, and fly through the air with no mechanical moving parts and completely silently. They look something like this when they fly around. This is ongoing work to improve the efficiency and thrust of these. So this is a large topic, and I'd like to say leading this space, and I think it's exciting stuff. But even if we have a propulsion mechanism, there are extreme resource constraints at scale that make it difficult to realize an autonomous robot. So one way to get around that is to create multifunctional components, pieces that take advantage of things like passive mechanical structures to produce communication strategies. And here we're looking at nature for inspiration, where a cricket, for example, produces a pretty loud noise using passive structures that have no resource overhead to incorporate. They're actually built into the wings themselves. And we can replicate this mechanism and get essentially free acoustic communication and sensing for our groups of robots in the future. Finally, on the front of artificial ecosystems, I believe that there's a large degree of specialization that we are not taking advantage of in the swarm space. In reality, social insects actually have a large amount of phenotypic diversity, which means that individual workers, for example, the leafcutter ants, specialize for tasks. So our platforms are not going to be incredibly versatile. We need to design different platforms that work together. So I think when you're looking at an advisor in grad school, there are at least three important questions. One is specific to me. The first is, why choose this research area? Why millisystems, microrobots? I think it's inherently interdisciplinary. It involves all the interesting parts of electrical engineering. It also touches on, materials, traditional mechanical engineering topics. It builds up a lot of skills, and the fact that these are systems that you're designing pretty holistically means that you are a full stack roboticist. You're not buying any piece of this off the shelf. You are designing it from the bottom up, and that builds a value. Finally, why work with a new assistant professor, someone who isn't there even before you? I think that it's a challenge in some ways, but it's also an opportunity. You'll have ownership over a new project. You'll have ability to work closely with me, which, for better or for worse. And you may even get to name the lab. Instead of Daniel Drew, we could have a cool lab name up there. We could take a vote. And why come to Utah? I chose to come there, and I like to think I make good decisions in life. It's beautiful. There are experts in practically every field, and there is an incredible amount of resources supporting research and the students. I'm excited, and I think you will be surprised and excited to be there as well. Yeah, so just reach out to me if you have any questions, want to talk. I'm at that email address at the top, or you can check out my website.
All right, thank you everyone for attending this virtual open house. I'd like to give a very brief summary introduction of my research. So I work in the intersection of machine learning and image analysis. And you might ask, why this area? First of all, images are ubiquitous in our lives these days. So there are so many sources producing a continuous stream of images, anywhere from your handheld phones and cameras to microscopes and healthcare devices that are generating a continuous stream of images which are just begging to be analyzed. And there's not enough human power, human time on Earth to analyze all of these images. And this is where our machine learning and image analysis algorithms can come in and help. So the research in my lab has two things. One is we try to make it grounded in applications. These can range anywhere from healthcare to security, and I'll give an example in a second. Second, we are trying to innovate in the space of machine learning and image analysis algorithms. So applications and innovation is what drives our interest in this area. All right, so I just want to highlight one example application to give a little bit of more context to what I'm saying. So we're collaborating with radiologists here at the University of Utah. And what we want to do is we want to use deep learning for screening for diseases. So you might know that radiologists are very time pressed. These days with COVID even more so, but even in normal circumstances, they can only spend a few minutes looking at a chest x-ray that comes before them. And they're going to look for evidence of things that the referring physician asked for this specific patient. For instance, they might have asked to evaluate, does this patient have pneumonia? So they're not going to spend hours looking at the image trying to figure out what every possible disease evidence there is in there. So this is where machine learning can help. We can aid radiologists, we can augment their reports, and we can automatically screen for diseases. So as an example, we chose chronic obstructive pulmonary disease, COPD. And typically COPD is diagnosed using something called pulmonary function tests, not chest x-rays. So a patient comes in, there's this device they blow into, they exhale, and you're measuring their lung function, right? So we want to ask the question, can we screen for this? Can we predict PFD exams from chest x-rays? So what we did is at our University of Utah hospital here, we went back and looked at all patients, gathered the data for all patients who had both of these exams within a certain time frame of each other, say a few months. chest X-rays, and PFT exams. Then we take a convolutional neural network, which is a state-of-the-art method in image analysis and machine learning these days, and we train it to take X-rays as input and predict the pulmonary function test values. In this way, now when we have new X-rays coming in, we can predict pulmonary function test values, even though that's not the primary interest for that patient. And we can see, according to the criteria for pulmonary function tests, does this patient fall into a risk group, and should that be further addressed? Now, that's the application side, but from the algorithm side, we're interested in kind of things, for instance, asking the question, the machine learning model, convolutional neural network in this case, made a certain prediction, but why is it making it, right? So don't just treat it as a black box, but can we build new models which actually, along with their predictions, also give you an explanation, an interpretation of why they made that prediction. Another thing we're interested in is to find, for instance, alternative ways to supervise the training of these models. The success of these models, to a large extent, depend on large amounts of data, and not just data, but manually curated data, labeled data. So imagine having hundreds of thousands of X-rays and then having each of them labeled as this X-ray has COPD or not. Then we can train a very successful model. But getting data, labeling data in this way is not feasible, right? So radiologists don't have time to label hundreds of thousands of images for us. So we want to be creative here, and what we proposed to NIH to do, and we got funded for this, for instance, is to use the existing workflow of radiologists and somehow tap into this in an unintrusive way to gather the supervision data we need. So what we do is, they're already dictating into a microphone their reports. So we just added eye tracking device on their screen, and we're tracking where they are looking at as they are dictating. Then we can correlate what they're saying with where they're looking at. And this, we believe, is going to give us a great way of actually training these models without additional data collection. Okay, so that is my brief summary. If you're interested, we're always evaluating and looking for excellent students. The work in our lab depends mostly on programming skills, computer-based experimentation, and also definitely math skills. So if you enjoy those areas, you might be a good candidate. And we have excellent computational resources to carry out this research in our lab. So if you're interested, feel free to drop me an email and we'll discuss. Thank you.
Okay, so I think you can all see the screen. So my research activities are divided roughly into 4 areas, illustrated in those quadrants. I'm just going to go through a couple of projects in each of those areas to give you an idea of what we've been doing the last couple of years and think about what's going to be going on in the future. In the area of neurophotonics, a lot of what we're doing is taking advantage of genetically engineered protein indicators to either control the activity of neural cells in the brain, or to image the activity of neurons in the brain. So for example, we're developing highly multiplexed implantable optical neural interfaces to take advantage of optogenetics, which gives us the ability to selectively address neurons by subtype, as well as through the wavelength of the light that we use for illumination. These devices are based on implantable optical waveguides. I may show a little more detail a little bit later if I get to it, but we're trying to take light, deliver it through highly absorbing scattering tissue via implantable optical waveguides. We couple those waveguides to gallium nitride LEDs. We basically build small LED displays, connect those to arrays of waveguides, and then implant those devices, and then look at the spatial temporal control of neural activity. On the imaging side, we're taking advantage of the fact this whole process can be reversed in the sense that we can collect light through that same array of waveguides. And not only can we collect light, we can also collect images. So this is a project with Professor Menon, taking his work in computational microendoscopy and translating that into doing wide field endoscopic imaging in the brain, using the fact that each of those optical waveguides in itself can generate an image of, fluorescence image of activity in the brain, and then we can produce a composite image by combining all those individual images. And all this is done via training of convolutional neural networks. Another area of research in the group is optical to terahertz light matter interactions. A lot of this is based on ultrafast techniques. Two recent projects I'll describe here based on the spectroscopy of perovskite materials, which are highly efficient optoelectronic hybrid organic and inorganic materials. Their big advantage, besides high efficiency, is very low cost. But there's a lot that we don't know about these materials for broader applications beyond photovoltaics. Interestingly, some of these materials, the Rotoston popper type, can naturally form multi-quantum well structures. We can control the thickness of the quantum wells by the number of lead iodide layers in the structure, but these are not pure phase structures all the time. Right? We ideally would want to have quantum wells of very uniform quantum wells throughout the thickness of the multi-quantum well stack. That doesn't happen. We can have high temperature phase, low temperature phase. We can have mixed phases. So we've used a combination of electroabsorption spectroscopy and more conventional optical spectroscopy of the excitonic features of these quantum wells to then determine what the phase composition of these materials are as a function of the quantum well, or I should say the intended quantum well thickness. And hopefully this will help design better optoelectronic devices in the future. Another area is taking advantage of the splitting of spin current due to breaking of inversion symmetry in these two-dimensional perovskite materials. This definitely gives rise to applications in spintronics. And what we study is the selective excitation of these spin currents via ultrafast optical excitation, and then looking at the terahertz emission from those spin currents. And we do that as a function of input and output polarization states, as well as input angle. We can learn more about those materials, as I mentioned, for spintronic applications. In the area of UV photonics, we've focused a lot on UV plasmonics, which is the use of deeply subwavelength structures, producing a very strong, tightly confined resonance response in the UV spectral regime. Some recent work there was looking at the chiroptical response, sort of an engineered chiroptical response of aluminum nano antennas in the ultraviolet. Chiroptical response consists of optical activity and absorption contributions. And we have ways of engineering both of those to try to enhance chiral selective spectroscopy, which is extremely important in the UV regime when you're dealing with biomolecules. Another kind of related area really sort of shows you some of the capabilities we have in our nanofab in terms of surface analysis and imaging, is when we make these very small structures. So remember, the ultraviolet, we're talking very, very short wavelengths, below 300 nanometers. So any type of optical structure that we build for these wavelengths is, in the tens of nanometers in size. So we need to really be able to do metrology of our structures on the nanometer scale. So we do have very nice imaging capabilities to be able to do cross-section as well as elemental analysis on the nanoscale to see, not just what we thought we made, but to see what we actually made and be able to analyze that and then introduce the results of that analysis into our simulation models to better predict the response of those structures. Then finally, in the nanophotonics realm, some recent work there has been looking at dielectric multi-layer stacks, 1D photonic crystals. We've done this both for visible as well as ultraviolet wavelengths. But very recently, we've looked at the contributions of what we call bound surface waves, which are literally bound to a terminating layer at the top of the multi-layer stack. as well as internal modes, which are due to the band edge resonances of the photonic crystal. And we found from radiation patterns, very, very narrow radiation patterns produced by bound surface wave coupled emission, broader radiation patterns produced by the internal emission, but also by using a combination. Since they produce different radiation patterns in the far field, we can use those radiation patterns to actually determine how far the fluorescent emitter is from the surface of the photonic crystal, which is kind of an interesting kind of three-dimensional imaging capability we have for fluorescent species. Another recent project is developing some plasmonic metasurfaces we're basically building dipole antennas on a very small scale, making those antennas from different material compositions in order to encode grayscale images based on the composition of those dipole antennas. And again, these dipole antennas on the order of 100 microns, or sorry, 100 nanometers in size. To very quickly just run through this neural interface work, the idea is that we can use implanted optical waveguides to deliver light millimeters into tissue, which is beyond the typical attenuation depth, largely due to scattering in tissue, scattering of light in tissue. We do that by making miniaturized indium gallium nitride LED displays. This shows a close-up of the display coupled to an array of optical waveguides, produce a packaged device. We can then spatially temporally modulate the light pattern produced by that device. We carefully engineer the light projection properties from each of these waveguides so that we project the proper distance in the tissue with the proper intensity. Just showing some images there in a laboratory environment. And then we can implant those in a non-human primate brain, perform electrical recording, and show that we can selectively do at depth excitation and control of neural activity, controlled by the pattern of light, as well as controlled by the intensity of light. So this is one of our major ongoing projects in the lab. So I'll stop there.
So yeah, I am Masoud Parvani. I'm an associate professor and associate chair of the department. So I do research on smart infrastructure, specifically looking at power and energy systems, as also they connect to the rest of the infrastructure, including electrified transportation, water infrastructure, and gas infrastructure, as well as communication systems. So yeah, I have a fairly large lab. We have aside from me, we have Dr. Jairo Giraldo and Dr. Mohammed El Hariri, who are research assistant professor in the lab, and we have senior research associate Dr. Gilani Farah and Dr. Bosan Lee. Plus, we have like a multiple PhD student in the lab, but that doesn't mean that we are full. We are always looking for more students to join our lab. In terms of research project, we do research, as I said, on the smart infrastructure. Specifically, we are looking at the flexibility of power and energy systems, as well as the cyber physical resilience of these systems. We look at how we could integrate energy storage devices in the system. You hear all the news that energy storage is the next boom in the energy industry. You hear all over the world that this is like 100 megawatt battery in Australia by Tesla, or like somewhere around the world. That's what we are doing. We are developing models, scheduling and pricing models in order to integrate in a cost-efficient way the energy storage in the systems. We are also one of the pioneers, the research group, looking at the intersection and interconnection between the power and water systems. And there are a lot of like interconnection between power and water system from generation side to the demand side. In addition, that we are also working on the transportation electrification. So here I would like to show a few of the like tools that we have developed. So this tool, I don't know, do you see that, or this is like going to another tab? Okay. So yeah, so for example, we have developed this tool that tries to co-optimize the airborne power and water distribution system, and this is a tool we have developed to visualize that co-optimization, to show how, like for example, a change in the power consumption or like interruption in power consumption can result in interruption in the water consumption and so on. We have, in addition to that, we have developed tools for if this goes back here, like for the electric for transportation, how like how electric vehicles, specifically how electrification of the transportation sector could impact the power sector, because now like kind of power system is becoming a like gas station for the transportation sector. That's what we do. We have developed again other tools that, for example, one of the most recent tools that we have developed looks at how transit system, public transit system, bus transit system, if electrified, could impact the power distribution system. For example, you see that like buses could charge along the way rather than like being one of the most pollutant bodies in the city. They could charge along the way, but also they would also affect the power system infrastructure. So that's what we are doing. We are trying to develop models that would manage that interaction between the transportation and power system. And so in addition to the research, we also do a lot of events. So for example, we have recently started Utah Resilience webinar series that we bring together like industry leaders in order to make sure that we are interacting the research between the industry and the academia. We also make sure that we are connecting the students with the industry, and so for that we have developed this Utah Power and Energy Career Expo that we bring industry together with the students in the same room. They sit together, they talk, and but the sit together was for the part that we didn't have coronavirus, so maybe next time we sit together would be in fall, but actually we are going to do that next time as a virtual event, so which kind of also provide opportunities for more students to attend. So yeah, again, excited to see many of you here, and please feel free to contact me if you have any questions. I would be happy to talk to you and see if you are a good fit for my lab. And as I said, we are always looking for smartest and brightest student to join us. Thank you.
So my name is Pierre Guerdon. I'm an associate professor in the department and associate chair as well. And my research is about computer engineering at large. I like to say it that way because we try to bridge the gap between all the subdomains of computer engineering and look at the interdisciplinary aspects of it. For instance, and I will invite you to just browse the website and you can see an overview of the research we do. We have a very broad set of activities ranging from the exploration of new device technologies, including nanofabrication of those devices and studying all the impact of those devices from a circuit and architectural perspective. At the same time, at new tooling and new types of architectures. We are very active on the open source hardware scene and are the actual leaders in open source FPGA. So we build completely open source hardware architectures, so hardware FPGAs and software tooling for that. I will invite you to go and look at our GitHub page. You can see all the projects we have right there and the various documentations. Always happy to have people poking around all the stuff we do there. At the same time, we also explore new types of embedded systems, and we have a very large activity around air quality monitoring and smart city threat detection. So we do monitor in real time pollution and chemicals of interest with new types of sensors, new ASIC architectures to interface that, and new machine learning technologies for that. So I invite you to just browse the website, lnis-uofu.com. You can also reach out to the various people in the lab if you have any questions. We do have also a fairly large lab, so there's quite a lot of resources you can ask for among the students. And as you know, we're always looking for bright people. So you're welcome to reach out to me. We'll be glad to talk. Let's keep the discussion open. Thank you very much, folks, and I hope you had a great morning.
Thank you very much, John. Good morning, everyone. So I am Fatima, and I did both my master's and PhD at the University of Utah. So I came here in January 2015, and to be honest with you, I had a little bit of a cultural shock because it was winter, it was cold, and I used to live in very crowded cities like Beijing and Tehran. But after a while, I started really liking it here, and here are the reasons. Well, okay, first of all, the University of Utah has a very good quality of education, and you have already listened to faculty presentations, and I'm sure that you have checked some of our faculty papers, and the classes were really amazing. But there are other aspects that made University of Utah kind of like a unique place for me, like a full package for me. For example, nature. With just 10-15 minutes drive, I used to go to a river in Mill Creek Canyon and sometimes meditate, or just go to the parking lot of Merrill Engineering Building and see the sunset and the whole valley. It is an amazing view, and it was as if I am right in the middle of nature. And it was very important for me. In fact, at some point I checked, Utah is in the top 5 most beautiful states in the United States, with 5 national parks that each one of them, the nature is different and very beautiful. And this is just Utah. Also the neighboring states that within like some hours drive, like 4 to 5 hours drive, like for example, Wyoming, Colorado, like Arizona, they have some of the most famous national parks in the whole world. It's just the beauty is astonishing. And I really hope when you come to the University of Utah, you get a chance to explore the rest of the United States. And Salt Lake City has a great location to do that. University of Utah, basically. And if you don't like outdoor, if you don't like nature, well, Las Vegas is just 4 or 5 hours drive from here. But also Salt Lake City is a metropolitan city. It has a lot of cultural activities, a lot of art activities like operas, concerts, theaters, like dance performances. I went to some of them and they were really nice. And basically with our student card, University of Utah card, they are either free or very affordable, very cheap. And there is also a diverse community here from different countries, different cultural backgrounds, and even different religious groups. And diversity was also important for me. In fact, I had a friend of mine, he went to a state that it has one of these Ivy League universities there. And he came back and told me, Fatima, be grateful. There are university towns that they don't even have downtowns. And I was thinking, yes, we are lucky to be studying in here, to have all of these things at once. And the other good thing about here is that, you know, the cost of living in here is not that high compared to, for example, California. And, you know, when you study your PhD here or your master's here, well, your salary is kind of limited. Yes, when you go and find a job, of course, you're going to make a fortune. But as a PhD student, the budget is limited. But I managed to have a relatively comfortable life in Salt Lake City with my PhD salary. I visited several places and I really enjoyed them. Just one thing, please don't get me wrong. I'm not saying that PhD life is going to be easy. Studying masters is going to be easy. I don't think it's easy anywhere in the United States. But what I am trying to say is that, you see, this place, University of Utah, has a combination of different things. It was like a full package for me that can actually help you to make a balance in your life in here when you do your PhD, that can help you, University of Utah can help you to try and learn new things, different things in life. Like, for example, I attended different conferences, symposiums. I even actually got involved in business projects at Adolescent Center. I attended mini lectures and learned about management, strategy and marketing, finance, accounting, and many other things. And these were all possible at the University of Utah. It has been a great experience for me and I really enjoyed it. And I am very grateful to the ECE department. They have been really nice to me. I am thankful. And I sincerely wish you also have a very good experience at the University of Utah. And I know when you go to a new place, it might sound a little bit lonely. Well, change takes a lot of energy, and I will be happy to help you or assist you if you don't know anyone from your community. In fact, I know different people from different communities in here. I'm going to actually put my email in the chat, and feel free to contact me. And sincerely, I wish you all the best. Thank you very much.